Welcome to the LSU Department of Chemistry. Behind me we have 3 of the buildings that house our entire department. Right behind me is Virginia Williams Hall, and that is going to be our teaching building where as a graduate student you would take classes, and also TA labs up on the 3rd floor. We are about to next walk over to Chopin Hall, which is going to be the first of the 3 buildings that we'll go take a tour through, and you can see all of our facilities and labs in there. So now we're in the Polymer Analysis Lab, where we have our expert, Dr. Rafael Cueto, who will talk to you about all the different types of instrumentation we have in here to analyze polymers.
Okay, so here in the Polymer Analysis Lab, we have different types of instruments, mostly for molecular weight characterization and size characterization. Here on this side, in front of me, we have what's called GPC or SEC. This will be for size separation and molecular weight characterization. The unique features that we have here is that we don't do regular GPC that will be done with the standards. We do absolute molecular weight characterization using multi-angle light scattering detection and concentration detection. That allows us to do molecular weight distributions and size distributions that other labs can do. So we have different types of instruments. We have organic GPC with DHF, toluene, or we can change other solvents. We have aqueous GPC, and aqueous will be any form of aqueous solvent. So we have different buffers or different salt concentrations. And for the separations, we'll have also different types of columns depending on what type of molecular weight size you want to measure, from small, medium, and very large. In addition of having a GPC, we have something that is called AF4, asymmetric flow-field-flow fractionation. It's another kind of a size separation, but on that we can do also particle separation, and with the same type of detection, light scattering and concentration, we can get molecular weight and size distributions. On this side, can I move? Yeah. On this side we have thermal analysis, and for thermal analysis we have TGA, thermogravimetric analysis, we have DSC, differential scanning calorimetry, we have DMA, dynamic mechanical analysis, and we also have some rheology on this side. So on this we are going to measure properties of polymers or particles. Depending on temperature, we can measure composition, decomposition, thermal events, glass transitions, crystallization, crystallinity, melting. DMA, we are going to measure modulus, in some cases glass transitions. Rheology, we are going to measure all kinds of rheological properties. In this corner, we will have some other types of light scattering, and what we have here is a Z-sizer. On this, we can measure size by dynamic light scattering, or we can measure zeta potential, which is an indication of the charge on colloidal particles. We have another lab that we have a research grade DLS, dynamic light scattering, that we can do multi-angle light scattering and multi-angle static light scattering. With the detectors that we have here for a GPC, we can also do what's called batch measurements. That will be offline measurements of particles or molecular weight characterization of polymers. That will be in a batch mode, and on that we can do things like sim plots and divide plots that will give you some other information. Okay, that's like the basics that we have here. We have some more things.
Alright you guys, we are about to go and walk into our X-ray crystallography center. Now before we go in, I wanted to introduce you a little bit to know who our crystallographer is. We are really fortunate to have in-house Frank Franzak, who is a fellow of the American Crystallographic Association. Particularly recently, he was named a CDS hero by the Cambridge Crystallographic Data Center. So he's a really huge deal in the crystallographic world. He's had 3,300 entries into their database since 1975. He recently, in the biggest year he had was 465 entries in 1 year. In that same year, he published 384 articles. So a really, really big person in the crystallographic universe. In fact, so much so that they even nicknamed his 1000th molecule that they submitted as the CDS man. So without further ado, let's go in. This is Dr. Frank Fronzak. He is the expert in charge of our X-ray crystallography facility.
Hi, welcome to the Xray Lab. I'd like to show you what instruments we have and give you an idea of what we do here. We have two single crystal X-ray diffractometers. And what we do is we shoot X-rays at a very tiny crystal, about the size of a grain of salt or sugar or something like that. You can probably not see that one on the top of a little fiber here. But anyway, that one of those is in the center of that instrument. We have an X-ray tube that shoots X-rays at the crystal. The X-rays are scattered into a diffraction pattern, and the main job of this instrument is to measure the diffraction pattern, the intensities of all the many tens of thousands of X-ray diffraction maxima that we get from that single crystal. Now, if you look over here, you'll see the image from the detector on this diffractometer, and you will see there are lots of spots here, white spots. Some of them are very bright, some of them not so bright. There's a wide range of intensities, and we measure tens of thousands of these. I'll put this on a little kind of movie thing, and you'll see all the different images we've gathered there. So over a matter of several hours, we will gather all those intensity data, measure all the intensities of each one of those spots, which are maybe tens of thousands. And the nice thing about that set of intensities is that when you take the Fourier transform of that set of intensities, you get three-dimensional electron density within the unit cell of the crystal. And the nice thing about three-dimensional electron density in the unit cell is that it's pretty close to zero most everywhere, except where there's an atom. Right? And we get a peak in the electron density at the three-dimensional coordinates where there is an atom. And of course, the size of the peak depends on how many electrons there are in the atom. A cobalt atom will have a much bigger peak than a carbon atom will, for instance. So we can find the three-dimensional coordinates of all the atoms within the unit cell, and we can see which ones are close enough together to have covalent bonds between them. And we can come up with a mathematical model of the molecule which is packed into making up the crystal. Let's see, if you look at another thing I have here, this is the results of one such experiment we did a little while ago. And you'll see there is a molecule there. All right, we get three-dimensional coordinates for all these atoms in the molecule. The gray ones are carbon, the blue ones are nitrogen. That yellow one there is sulfur and so on. So you can see there's a tremendous amount of structural data we get from this. To begin with, we identify what the compound is, which is what a lot of people want to know. But besides that, we get all the bond distances and angles. We can identify the atoms, tell what kind of bonds we have, single bonds, double bonds, and so on. We can look at intermolecular contacts. For instance, this is a water molecule with hydrogen bonded to nitrogen there. So from this really extremely tiny sample here, in a matter of sometimes just hours or maybe a day or two, we can get this tremendous amount of structural information about that particular compound. The way my laboratory runs is usually graduate students walk in and bring me a little vial that's got some of these crystals in here and just leave it to me to provide all the results. We make no charge for this at the moment. Can't promise that'll always be the case. Or if research directors are okay with that, we can also teach individual graduate students how to do this themselves, or anywhere in between. I can collect the data, give it to the students who know what to do with it. They can do all the calculations, anything in between. So that's what we do, and Sorry you couldn't make it to visit us in person, but I hope this helps you understand what we do in this laboratory.
Hey guys, so now we're standing in front of the Chemistry Materials building, which is one of the 3 chemistry buildings that we have just for the Department of Chemistry. This building right here was built in 2012, and it houses mostly, which is named Chemistry and Materials, some organic synthesis, some material synthesis. It also houses some of the facilities that we're going to see in there, namely the Shared Instrument Facility, which is called SIF, the Mass Spec facilities, and the NMR facility. All right, you guys, we are now in the Shared Instrument Facility. This is on the first floor of the Chemistry and Materials building. And this is an instrument facility that is a collaborative endeavor by multiple departments. Biology uses this, chemical engineering uses this, and a few other programs depending on what their needs are. It houses several different instrumentation. So we're going to walk down the hall and meet Dr. Dongmei Cao, who will give you a tour of all of the different types of instrumentation that we have in this facility. Dr. Dongmei Cao.
Yeah, thank you for the introduction. I'm the director of Shared Instrumentation Facility. For a quick general introduction, and this facility hosts a suite of light microscope and electron microscope and some other like a chemical analysis instruments. So we provide education and research support for LSU, other university, and industry users. So here I want to show you 2 light microscope, and this one is from Leica. It's called DM6B fluorescence microscope. People use this one for tissues, soft cells imaging, and this one is from DICE. It's called a stereo fluorescence microscope. We use this one either for bright light imaging or fluorescence light imaging. Newer fluorescence microscope from Leica. It's called SP8, the model. Basically, the confocal is realized by the pinhole. It's like a mechanical device. And the other one I showed you earlier, DM6B, is also confocal light microscope. That one is realized by software. This instrument is called Xray photoelectron spectroscope. So basically, this one we use it for chemical information analysis. It's a very surface analysis of your samples. It happens in the 1 to 10 nanometer surface layer. So it basically gives you the information about what elements you have in your material and what's the chemical status. Okay, in this corridor, we have 4 electron microscopes I want to show you. We have 2 SEM. Scanning electron microscope. This is one of them, and this SEM not just the electron column. We also have focused ion beam, so it's called a dual beam system. With this system, we can do the very surface morphology imaging, or we can do nano or macro fabrication with the focused ion beam. With this instrument, we also have EDS detector and the EBSD detector. So we can do the chemical analysis or structural analysis, like whether what type of crystal they are and orientation, those detailed information. We have another SEM. If you look closer, and this is from gel. It's a tungsten filament. Big difference between this SEM and the other one I show is the electron source, and this one is from tungsten filament. The other one is a field emission. So field emission always provide better resolution, and this one is it's still okay, the resolution. So we use it for mostly like a soft material, like tissue cells after you fix it and prepare in a certain way. So it's for SEM ready. This is a transmission electron microscope from gel. We have 2 TEMs here at SAFE, And this is 200 kV. We call it a high resolution TEM. Basically, we use it for mostly like a solid matter. The sample has to be very stable under electron beam. We do the lattice fringe imaging or particle size evaluation. When you have very nanoparticle, like a very small nanoparticle, several nanometer, you can use this one to check, even can see whether they are crystalline or amorphous. We can also do the EDS analysis on the material you are looking at. Yeah. In this room, it's another TEM. This is basically optimized for soft matter material. Like they operate at 120 kV. It's lower kV, so it's gentle to the samples, reduce damage, sample damage. We also have the cryo capability with the cryo plunge to prepare your sample, and you can check the sample like in a frozen status. The big lab is basically for sample preparation, and we have a TM expert and busy here most of the time, prepare the sample. Whether you want to check it under SEM or TEM, you have to prepare your sample, get it ready for SEM or TEM. Here in this room, we have 3 major equipment, and this one here showing Renaissance, that's the Raman microscope. Basically, we use the user to check your sample, and by checking the spectrum, actually it's like a fingerprint of people. Each people has their own fingerprint, and each material has their own spectrum. So we have 3 types of laser: 532, 633, and 785 nanometer. For the user to choose when you work with different material, and one specific laser will work well. So you can choose that. It's pretty easy to operate, and after you got your data, you can compare with the data library and find out what type of like a function group your material belongs. And this instrument is called Xray Diffractometer. It's from Melbourne Analytical. The model is M-Pardon. And people use this one to check the crystallographic information about your material. So we have different types of holder. We have the, right now, this is called a RTS holder. We also have light sample holder and also the pipette stage. So we can work with different types of material, whether it's a solid or powder, or air-sensitive material, or single crystal. So we can, check a wide range of material and find out what crystallographic information about your material. Yeah. XRF. So it's for chemical analysis of your material. We use X-ray to interact with your material. By checking the characteristic X-ray, we can find out what elements in your material, what's the composition.
All right, you guys, now we are in the second floor of the Chemistry and Materials building, where not only are there tons of research labs, but there is also our 2 main user mass spec facilities. One of them is where you're going to meet Connie David. She is in the ion trap mass spec facility. And then the other one, we're going to go down the hall right after that, and we're going to go meet Dr. Fabrizio Donnarumma, who is in charge of our other mass spec over there. Hi, guys. We are now standing in one of our 2 mass spec facilities. Actually, there's probably more than that. This is Connie David. She's one of our staff scientists in the mass spec facility, and I'll let her tell you about her instrumentation.
Hi, this is where you might come to submit a sample if you needed to know the accurate mass of your sample. If you were to come into my lab, you would come here to this little station, get a label, submit your sample, sign a submission form, and then I can run your sample, or if you want to learn to become a user, I could teach you to run your own sample. And the instrument that you would be using is this ESI TOF, or electrospray ionization time of flight instrument. It's an accurate mass instrument, so especially if you're an organic student in our department, you would be submitting your samples here for analysis and verification that you did synthesize the compound you were trying to synthesize. I can generate formulas from a spectrum, and you can use this information for publication purposes. If you decide that you want to become a user, I can train you to run the instrument yourself. I can also train you to look at your own data so that any instrument that you have to use now or in the future, you would be able to interpret your own data, and this is very valuable. Besides the ESI TOF accurate mass instrument, we also have a GCMS instrument that's available for your use, and again, you could become a user of that instrument as well. We have other instruments. My colleague Fabrizio will be explaining those to you, I'm sure. Feel free to send out any questions you might have.
Alright, hi guys. We are now in our other half of the main mass spec facility on the second floor. This is Dr. Fabrizio Donnarumma, and he will tell you about the mass spec standing right behind us.
Hello everyone. Now this is our Orbitrap instrument. Is the new addition to our portfolio of instrument. It's an instrument that we use most of the time for proteomics, bottom-up proteomics. If you want to know the composition of a sample from the point of view of proteins, this is the instrument you want to look at. It works with nanospray, and I will show you very quickly what is a nanospray. It's that spray there. And it has an LC system that delivers nanoflow rate 300, 400 nanoliter per minute. We use this instrument as a workhorse for proteomics, but from time to time we also use it for intact proteins or for other small molecule analysis. On the back we also have another instrument, an ion trap. It's also connected to an LC system, but use that instrument mostly for protein analysis and for small molecule analysis in a mode that is called MRM, multiple reaction monitoring. Basically, what you can do here is liquid chromatography mass spectrometry of any kind. In addition, on my left, which is not visible from here, but you have an entire wet lab dedicated only to mass spec sample prep. And you can come here and do the sample prep here so that you don't have to worry about the right chemicals or the right procedure. I will actually help you develop those procedures, validate them, and execute them. So I hope you will join us soon, and that's it.
Now we are inside of one of the organic research labs inside the chemistry and materials building. This is some of the newer labs that we have. Again, this building was done in 2012. There are lab bench spaces available, hood bench spaces available, and there's even glove boxes depending on the type of research. Now this is Dr. Semin Lee's lab, so this is his postdoc working in the glove box, but this is an example of one of the labs that we have for you to do research in. Now we're on the third floor of the chemistry and materials building, and I'm about to walk into the NMR facility that we have here. Now, we have two state-of-the-art 400 megahertz machines, mostly used for just routine organic and inorganic analysis. We also have a 500 megahertz NMR that is equipped with a cryogenic probe, and this is really, really helpful for doing protein analysis and other biological molecules, so you can get that really, really high level of sensitivity. These are about the types of instruments that you would find in current R&D labs across the U.S., and so these are really the top of the line and we're lucky to be able to have these here. This is now the end of the tour for the chemistry department facilities and labs here at LSU. Thank you so much for sticking through to the end. We really do look forward to hopefully having you here in person, but for now, thank you for being patient and dealing with this virtual version. If you need to reach out to any of the facility staff, please let me know. I can give you the contact information for them if you have any other questions about the instrumentation. And that's really it. Thank you again, and go Tigers.